For our new lesson, bolted connection. Introduction. A bolt is a metal pin with a head formed at one end and shank threaded at the other in order to receive a knot. On the basis of load transfer in the connection, bolts are classified as first, bearing type and friction grip type. Types of bearing bolts. There are two types of bearing type bolts, namely unfinished or black bolts. The shanks of black bolts are unfinished, as obtained at the time of rolling. For black bolts, diameter of bolt hole is larger and are used in most of the work. A black bolt is represented as M16, M20, or etc., which means black bolt of nominal diameter 16 mm, black bolt of nominal diameter 20 mm, and so on and so forth. Next, finish or turned bolts. Turned bolts are obtained by turning hexagonal shank to circular shape. The bolt hole diameter is only 1.5 mm larger than that of the shank in case of turned bolt. These bolts are used in special jobs like connecting machine parts subject to dynamic loadings. Types of bolted connections. Types of joints may be grouped into the following. First, lap joint. It is simplest types of joints. In these, plates to be connected overlap one another. And the other one, butt joint. In this type of connection, the two main plates about against each other, and the connection is made by providing a single cover plate connected to the main plate or by double cover plates, one on either side connected to the main plates. So here's the example. This is the lap joint, which means there's overlapping of two plates, and this is your bolt. While the butt joint, you have a cover plate and the two plates, and you have the bolt. And classification based on type of force in the bolts. So first we have the lap connection based on single shear, and this one is the double shear. Formulas for shear of rivets. We have T for tensile force is equal to the area of the shear multiplied by the shearing stress, and the area for shear is equal to pi d squared over 4 times n, where S sub S is the shearing stress of rivets, which is for single shear, n is equal to the number of rivets, and d is the diameter of rivets. So this is the hole with the diameter d, and we have the force PS, or it is T for tensile force, pairing of rivets, and the formula is T is equal to A sub B times S sub B, where A sub B is equal to D times T times N, where D is the diameter of rivets, T is the thickness of plates, N is the number of rivets, and S sub B is the bearing stress of rivets, which means the area for bearing is equivalent to the diameter times the thickness and multiplied by number of rivets. So in this case, we have the projected area of the rivet hole, and that's for bearing of rivets. Bearing of plates, and the formula is T for tensile force is equals to A sub n times S sub T, where A sub n is the net area, and it is equal to open parenthesis H minus twice of D, close parenthesis, times T, where D, the big D, is equal to the small d plus 3 millimeter, where the small d is equal to the diameter of rivets and T is equal to the thickness of plate, and A sub n is the net area, and S sub T is the allowable tensile stress. So in this diagram, we have P sub T, or the tensile force, and the tearing of the area, which is the net area, is the width, which is h, minus twice of the diameter and multiplied by the thickness of the plate. And to find the efficiency, it is equal to the safe rivet capacity over full strength multiplied by 100, where safe rivet capacity is equal to the smallest value of T, or the tensile force, while full strength is equivalent to A sub G multiplied by S sub T, and the area gross is equal to T multiplied, or the thickness, multiplied by the H, or the width of the plate, and multiplied by S of T, or the tensile stress. So here's the example. The longitudinal joint of a boiler having 14 millimeter plates has a strength of 400 kilonewton and a pitch length of 400 millimeter. The efficiency of the girth joint is 40% and the allowable tensile stress is 80 megapascal. Determine the maximum diameter of the boiler if it designed to operate at a pressure of 1.6 megapascal. So this is a boiler with a thickness of 14 millimeter and with a pitch of 400 millimeter, and we need to find the diameter of the boiler, or the maximum diameter of the boiler, with force T of 400 kilonewton and the tensile stress is 80 megapascal with a pressure of 1.6 megapascal. So the given are thickness, which is 14 millimeter, and the tensile force, which is 400 kilonewton, and the pitch, or the S, is also 400 millimeter. Then the efficiency is 40%, or equivalent to 0.4. Then the tensile stress, which is 80 megapascal, and the pressure, which is 1.6 megapascal. So based on the diagram, if you cut, we have the tensile force at the left side and another side, which means we have twice the tensile force is equal to the force acted, and the force based on the pressure is the pressure times the diameter multiplied by the pitch, and this is twice of T, and then we substitute. So 2 times 400 in terms of Newton, it should be 400 Newton, 1000 Newton, is equal to the pressure, which is 1.6 megapascal, with the diameter, which is the unknown, and multiplied by 400 millimeter. And then we equate, which means D is equal to 2 times 400, 1000, divided by 1.6 times 400. So let's check based on the given. So 2 times 400, 1000, divided by 1.6 and 400? The answer is 1250, and it is in millimeter, or in terms of meter it is 1.25 meter. Next, based on the given, we have a 40% efficiency with a variable of stress of tensile stress of 80 megapascal. So based on the force, which means all the forces perpendicular to the surface, we have the function of the efficiency is T is equal to the force. And based on the efficiency, the E multiplied by the strength tensile stress, and based on the area, the area of the tensile stress is base cross-sectional area is the circumference of the circle multiplied by the thickness of the plate, and it is equal to the force P, or the pressure, multiplied by the area of the shear, which is pi over 4 d squared. Then we substitute the efficiency is based on the given, it is 0.4, and the tensile strength or stress is equal to 80, and we'll multiply by pi and times d, and the thickness is 14 millimeter, is equal to the pressure design, which is 1.6, and pi over 4 d squared, and we cancel out d and pi, and what is the diameter? So 0.4 times 80 times 14 divided by 1.6 and multiplied by 4. And what is d? So let's check. So 0.4 times 80 times 14 times 4 and divided by 1.6, and the value is 1120 millimeter, or it is 1.12 meter. The maximum diameter is equal to 1.25 meter. Here's another example. A tension member is made up of 10 millimeter thick steel plates, 225 millimeter wide, by a lap joint made with 3 toes of 20 millimeter bolts using snug fit in drilled holes and arranged in the pattern shown. This one. The permissible stresses in the bolts are 138 megapascal for tension, and the net section 110 megapascal for shear, and 220 megapascal door bearing. Assume diameter of hole equal to diameter of bolt, and then find the maximum permissible tension on the plates and the efficiency of the joint in percent. We have 8 bolts, so we need to cut every section to find the value or the permissible tension. First, given we have the thickness of the plate, which is 10 millimeter. Next, the width, which is 225 millimeter, which is the lap joint, and the diameter of the bolt, which is 20 millimeter diameter, and the stress for tension is equal to 138 megapascal. The stress for shear, which is 110 megapascal, and stress for bearing, which is 220 megapascal. Next, the stress based on the gross section, which is 225 millimeter, and the thickness, which is 10 millimeter. So for gross section, P is equals to tensile stress times the thickness and the width of the plate. We can find the value for P, which is equivalent to 138 megapascal multiplied by the thickness of the plate, which is 10, and the width, which is 225, or the P is equal to 307,740 Newton. For the tearing plate at 1 in this direction, we cut it out, and we have the force P1, which is the stress tension multiplied by the thickness, and the formula for tearing, which is H minus twice of diameter of the bolt. And the tensile stress, which is 138 multiplied by 10, and the height, which is 225, minus twice of the diameter of the bolt, which is 20, and close parenthesis. So 138 times 10, which is 1380, multiplied by 225 minus 220 is 40, or equivalent to 185. And then multiplied by 1380, or equivalent to, for the force P1, which is 255,300 Newton. Okay, why the tearing plate has the value is 2D? Because we have two bolts, 1 and 2, at section 1. So that's why we need to or subtract the tearing plate based on the bolts at section 1. So we have P1, which is 255,300 Newton. P1 plus, we have, if we cut section 1, we have 1, 2, 3, 4, 5, 6. So we have 8 bolts. So we divide the total value of P to number of bolts. In this case, we have 2, 4, 6, 8, which means in every bolt we have P over 8. 2, 4, 6 bolts, which means we have 6 times P of 8 in every bolt, which is equivalent to P. And P1, which is 255,300 plus 6 over 8, P is equal to P. P minus 3 over 8 is 3 over 4 P, equate to 255,300. And this is 1 over 4 P is equals to 255,300. 300. P is equal to 1,021,200 Newton. So we have at section 1 a value of P which is 1,021,200 Newton, or 1 mega Newton. And that's for section 1. At section 2, we have 4 bolts, and this is the diagram. So we have F2 or P2 and the force P. Same procedure, the tearing plate at section 2 is equivalent to P2. This one is P2, and it is equal to the tensile stress multiplied by the thickness and the tearing of H minus, we have 4 bolts, 1 2 3 4 at section 2, so therefore it should be 4 times diameter of bolt. And what is P2? Stress, tensile stress, which is 138, the thickness of the plate 10, and then multiplied by H, which is 225, less 4 times the diameters of the bolt, which is 20, and close parenthesis. And then we simplify. 138 times 10, which is 1380, multiplied by 225 minus 80, and the value for P1 or P2 is equivalent to 210 or 200,100 Newton. We check for the force P2 plus, for the bolt we have 2 bolts, which means twice of every force, which is P over 8, and it is equal to the total P. P minus 1/4 of P is equal to P2, and this is 3 over 4 P, and P2 is equivalent to 200,110 Newton, and P, 200,100 times 4 divided by 3, and P is equivalent to 268,800 Newton. And this is for at section 2. At section 3, in this line, and we have the diagram. We have 2 holes and the force P3 with a total P. Let's find the value for P3 for the section 3. We have a tearing plate, and the same concept, tensile stress multiplied by the thickness of the plate, and then the height of the plate minus, and how many bolts or the tearing plate? We have 1 2, so we multiplied by 2, and this is twice of the tensile stress is 138 multiplied by the thickness of the plate times the height 225, less twice of the diameter of the bolt of the tearing plate, and P3 is equal to it is equivalent to 255,300 Newton. Based on the diagram, the bearing of the plates, the shearing stress, based on the diagram, we don't have a bolt in between section 3 and the force P, and therefore P is equal to P3, or P is equal to 255,300 Newton, and this is for section 3. We'll find the shearing stress. And the shearing stress is equal to P is equal to 8. We have 8 bolts multiplied by the area of the rivets, and the shearing stress. And what is the value for the area of the rivet? So 8 multiplied by the area of the circle of the bolt, which is pi over 4, and the diameter is 20 and squared, and multiplied by the shearing stress, which is equivalent to 110, and P is equal to, for the shearing value of 8 rivets, and it is equivalent to 276,460 Newton. For the bearing load, for the bearing with 8 rivets, okay, P is equals to, we have 8 rivets multiplied by the thickness of the plate times diameter of the bolt and the shearing or the bearing stress, and 8 multiplied by the thickness of the bolt multiplied by the diameter of the bolt and multiplied by the bearing stress, which is 220, and P, 8 times 10, 80 times 20, it's 1,600, and times 2,220, and the value is 35,200 Newton. Based on all the forces from section 1, section 2, section 3, shearing stress P, bearing stress for P, and the maximum P that is permissible based on tension on the plates is equivalent to 255,300 Newton. The maximum permissible tension on the plates is equal to 255,300 Newton. Need to find the efficiency of the joint in percent, and E is equivalent to T over full strength, and the maximum tension on the plates is equivalent to 255,300, and we divide by the full strength, which is equivalent to, based on the gross section previously, we have 307,740, and we multiplied by 100 to get the percentage or the efficiency of the joint. So 255,300 divided by 307,740 multiplied by 100, and the value is 82.96%, and this is the efficiency of the joint in percent.